Okay, so today we're going to look at pulleys, which is the final section of this chapter. You might have noticed we missed out some of the questions in the previous section to do with lifts. We will come back to them. Don't worry, they're just my least favourite part of the chapter, and they're quite awkward, so we'll do them last once we've mastered everything else. I think it'll be easier if we do it that way. Also, if you've read your question list, you might realise that it's a bit of an obscure question list. That I'm asking you to miss out certain parts of questions, and that is because, just like with the connected particles, we had the kind of the basic stuff where it was the same every question, finding tension, acceleration, etc. And then we had the what I classed as changing criteria questions, where they're harder ones and they're different every time, and we had to recalculate the acceleration. The pulleys chapter does exactly the same stuff. It has some standard stuff, which we're going to look at today, and then the stuff that I've asked you to exclude, you'll probably see that they're like 7, 6 or 8 marks. That's the stuff where we have to start recalculating things, and that's what we're going to look at on Thursday. I think it deserves a lesson in itself. If you're really feeling it though, there's no harm in you attempting them questions, but I'm not going to teach you them today. So, what is a pulley? A pulley is a system that looks like this. We'll have a circle kind of at the top. That's the mechanical circle. We can imagine it spinning round, and it has a string that comes off either side. So if we spin the wheel around this way, this side will raise, this side will lower. And if we've got an object here and an object here, it looks a bit like a funny photo, I know, but that's just the unfortunate stuff of pulleys. If this is heavier and we release the system, then the right side will fall down, the left side will raise up. You'll see a better version in your textbook for this question. But the difference between a pulley and a connected particle is we can't just go ahead and model both of these obstacles as a singular particle. And that's because the particles are moving in different directions. So they'll never both be going up, they'll never both be going down. Because we always have an inextensible string, so this can't stretch. So they both can't drop down. They both have to stay at the same distance from each other. So we have to come up with a different way of eliminating tension in these questions, because in a connected particle we just modelled as a single particle. That got rid of the tension, that helped us find the acceleration. We need to come up with a new tactic in these questions, and I'll show you that. But we do know that the tension on either side of the model, so we will have tension, we'll have tension pushing up from the obstacle and pulling down from the pulley. Tensions always seem to point in towards each other. These tensions are all the same, and we know that under the criteria that this is a single piece of string and it's a smooth pulley. So a smooth pulley means that all the forces that kind of come through here aren't going to get disrupted by any friction or anything like that, and it will be the exact same round the other side. And by that we'll know that these will always move with the same acceleration on each side and the same speed on each side. So that's kind of all the technical stuff of pulleys we need to get out of the way of. And then we just need to look at how we would start labelling up our diagrams and answering these questions. So we've got a particle P and we've got a particle Q of masses 2m and 3m respectively. They're attached to the end of a light inextensible string, therefore that's just meaning we know tensions are the same, acceleration is the same, and the string passes over a smooth pulley. We'll only see smooth pulleys in year 1. And the string is taut. That means the string isn't kind of like an elastic band. It's not like stretchy or floppy or anything like that. The system is released from rest. And that's all they give us. We don't seem to have that much stuff here. We need to remember that when things are hanging, they are acted by gravity. So the weight downwards of this is the mass times by gravity. And the weight hanging down from this is mass times gravity. And here I'm just going to write it as 2 mg, 3 mg. I would never times it by 9.8 and then put that. I'd always just put the mass and then put a g on the end. They might cancel out later on, and it's always just neater to work in terms of g. But that's all the things we need to put on. There is one thing actually that is key. Always label on your directions of movement. We haven't been given exact masses, but clearly 3m will be heavier than 2m. So if this is released from rest, the system is going to move in this direction. This particle is going to fall downwards. This particle is going to raise upwards. And I know that these accelerations are the same. So, write down an equation of motion for P and for Q. All that is asking is to do an F equals ma for P and an F equals ma for Q. What I would always do here is resolve in the direction that the things are moving. So for P, I would resolve upwards because P is moving upwards. So when I resolve upwards, I do the motions that go upwards, which is tension, subtract the motions that are going downwards, which is 2 mg. That's going to get me my resultant force of that. And then mass times acceleration is just 2m for the mass and a for my acceleration. And then if I have a look at doing this for Q, if I do this for Q, because Q is moving downwards, I'm going to resolve these forces downwards. And you'll see why we do this in a bit. Makes it quite a bit easier for ourselves. But we always do that, don't we? When we do SUVATs, I always say, take your positive direction as the way you initially move. We always do this in mechanics because we know it's going to turn out nicer, easier values. So here, because I'm resolving downwards, I'm going to do the motions that are going downwards, 3 mg, subtract the motions that are going up, minus t. And then that equals to the mass times by acceleration. So that's part A done. That's all it wanted from us. Part B is asking us to find the acceleration. Well, we've got two equations above us. We should be able to use these to find the acceleration. We can't just model it as a single particle like with connected particles, so we have to model each separately and then pull a little bit of a simultaneous equations trick. Can you see when we resolve it in the way it moves, so one up, one down, we can see we get a positive t and then a negative t in there, and you're always going to get that because you're always just going to have tension, and tension's always going to be the same for both sides. So it's always going to appear positive in one, negative in another. So if we add the two equations together, add in this equation and number 1 and number 2, hopefully you can see that I'll do it out full this time, so t minus 2g plus 3m minus t. I've just done this, add this. Then on the other side of the equation, 2ma plus 3ma. Can we see here I've got a positive t and a negative t, so therefore tension is gone. I've lost tension out of my equation, so I can actually solve this for A now, and that happens every single time. So now I just need to collect this, 3mg subtract 2mg, that just leaves me with mg, and then 5ma. Well, I have m on both sides, so I can actually divide by m, and it's fine to do that because it's not an algebraic term, it's just a constant, it's just like representing a number, so I can happily divide by that. Now I need to divide by 5, so the acceleration equals to g over 5, or I might want to say a fifth g. I'd probably just want to leave it like that. Don't bother with decimals at this stage. You can if you want to, but I prefer not to. Okay, and let's have a look at part C. I'm going to have to definitely get a new slide for this. Now we just need to find the tension. So the tension, all we need to do is sub A into either 1 or 2. Remember, 1 or 2 of these equations up here. So just sub it back into one of these. Probably going to sub it into 1 because t is positive in here. I think that's going to be the easiest. So t minus 2mg equals to 2m times by a fifth g. Do a bit of resolving, etc. with this. Not resolving, just solving. You're going to get t equals to 12 over 5g. And I'll save you that step of algebra. Give it a go if you're not quite sure. Try and rearrange that, see if you get to 12 over 5g. So that's that part for C. I'm just going to grab another slide. Okay, so what have we got from this question? We've got tension, we've got acceleration. So when I get to my new slide, I will write out tension and acceleration. We got acceleration as a fifth g, and we've got tension as 12 over 5g. If I quickly get my diagram back, okie dokes. So find the force exerted on the pulley by the string. I always find this is a really awkward one, and I always forget what it means, but it's actually really, really simple. If we see that that is the force that's been exerted on the pulley, the things that are pulling directly down on the pulley, and it's just 2 lots of tension. So we just need to do 2 times by 12 over 5g, which is 24 over 5g. That is what has been exerted on the pulley. And it's nothing more complicated than that. Just look at your diagram and just think, what is directly pulling down on the pulley? We don't need to take into account this stuff down here. That is not directly pulling it down. That's kind of an indirect thing. This is the force that has been exerted straight onto the pulley. This 3mg and 2mg is what's being exerted onto the string by the particle. And then the final bit. Find the distance moved by q in the first 4 seconds, assuming that p does not reach the pulley. So the key thing that is here, assuming that p does not reach the pulley, that means that we're not doing a changing criteria question. If it reached the pulley, we'll talk about what would happen on Thursday. This just means that none of our information changes when we assume something doesn't reach the ground or doesn't reach the pulley. So whenever we're talking about kind of finding distance moved, we're given time, we're linking it back to a suvat. So find the distance moved by q, which is my particle on the right hand side, one that's going down, in the first 4 seconds. So distance is a question mark. It's been released from rest, so u is 0. We don't care about the final velocity. We know the acceleration is a fifth g, and we know we're looking for what it is in 4 seconds. So in this case, we're going to use s equals to ut plus half at squared. We're going to sub in all of this rubbish, and we're going to get out 15.7 roughly. We've used gravity in this, so we're going to have to call that 16 to 2 significant figures. And I'm not quite sure what units we're talking about. Meters, centimeters. I don't think it really specifies in here. Maybe meters. But yeah, that's that first question. Admitted a bit of working out there, but hopefully nothing that's lost some understanding for you. Okay, and then the second type of example we like to get in these is one where we have a less rude picture, and it's something over kind of a surface, and then one's dangling down. So you can just imagine something hanging off the edge of a table for this. I've got the diagram pre-drawn here because it's a bit messy otherwise when I'm trying to fit it all onto one screen. So the key thing is here, they've taken the information from the question, so A and B are the masses, connected by a light inextensible string. Particle A lies on a rough table, 4.5 meters from a smooth pulley, so I guess we could also label up that this is 4.5 meters if we really wanted to. And B is 0.5 meters above the ground, so we could label that up as well, with the ground being here. The frictional force of magnitude 0.08 G is on A, so I will do that off the back of A. And then it's obvious if we release this particle hanging is going to move downwards, so my acceleration goes down, and my acceleration goes across here. Again, with this, we can't really model as a single particle, and we want to avoid that in anything to do with a pulley. It's only connected particles that we can do that. That's because these are moving in different directions. One's moving down, one's moving to the right. They're moving in the same kind of flow, but it's still not the same direction. Direction means right, or it means up or down. This is going down, this is going to the right. That is not the same direction. You might sometimes work out the correct answer on a fluke if you model it as a single particle, but you won't be awarded marks if you do so. So, finding the acceleration, we've been told to jump straight in this time. I know from my experience with the last question, I need to set up two models with A and then B, and then I need to add them together to eliminate tension. So let's do that. For A, I'm going to resolve to the right because I'm moving to the right. So T minus 0.08 G equals to 0.4 A. And then for B, I'm going to resolve downwards because that's the direction I am moving once it's released. So 0.8 G subtract T equals to 0.8 A. Call this equation 1, call this equation 2. It's good to label up your equations because then you can just say, well, I'm doing equation 1 plus 2. You're showing what you're doing there. You can grab method marks up for that, and it's easy to follow your work. Rather than just saying adding equations, just label them up. It's helpful when you say subbing into equation 1, and then people know exactly what's going on. You can call them stars and crosses, it's up to you, but I just prefer to number them. So when I add these together, I'm going to get, I know the t's are going to cancel, so I'm going to get 0.8g minus 0.08g. So I'd get 0.8g adding on this negative, and then when I add up the two other sides, it will get 1.2a. So this is 0.72g equals to 1.2a, and then acceleration is going to equal to 3/5 g, which if you want as a decimal is 5.88. So I just divided by 1.2, didn't I? Okay, so let's leave that bit. Let's have a look at part B. The time taken for B to reach the ground. Well, for B to reach the ground, it needs to travel 0.5 meters to reach the ground. So again, we're talking about a time taken, we're talking about a movement of distance, we're looking at suvats. So it's moving 0.5, it started from rest, we don't care about the final acceleration. The acceleration is 3/5g, or 3/5 g I should say, and then the time, well, that's what we want to find out. So we're going to use s equals to ut plus half at squared, substitute in our values for this, we're going to get a quadratic for this one, and we're going to get two solutions. Obviously, you will pick the one that is positive. And when you do this, you'll get t equals to 0.41 seconds. So that's my answer to part 2. Omitting a bit of work there, but it's nothing I don't think we need to go through. And then part C, we'll ignore that one for now, because that leads on to Thursday's lesson. You might want to have a go at this question, so you might want to pause the video and then have a go at this question to check you've understood what's happened. Okay, hopefully you've had a go. I will release the answers. The first one you just wanted to show that, so you should have got there, and then known you've got there. And then find the value of k is 3, and state how you used the information the pulley is smooth, or the tension in the two parts of the string is the same. That's how we would use that it was smooth. If you said something about acceleration being the same, etc., that comes from the inextensible string bit, not the pulley is smooth bit. Okay, so take note carefully of the question list on Show My Homework, please, because I've asked you to omit a few things. But yeah, thank you, and I'll speak to you on Thursday.